Hi everyone, welcome back to the Heterogeneous Parallel Programming class. We're at lecture 4.7. We're going to wrap up the topic of the parallel scan pattern with more discussions. The objective of this lecture is for you to learn more about parallel scan. Especially, we're going to finish the analysis of the work-efficient kernel, and we're going to talk briefly about exclusive scan, and then we're going to extend the kernel-oriented view into a more complete library function that can handle large input vectors. So here we do a quick analysis of the work-efficient kernel. The work-efficient kernel will execute log n steps in the reduction step. And this should be very familiar to you. And each iteration will do half n, quarter n, all the way down to n addition. So the total adds is the simple series sum of 1 plus 2 plus 4 all the way to n divided by 2. And this series adds up to n minus 1. So the reduction step is of order n operations. And then it will execute log n minus 1 parallel iterations in the post-reduction reverse step. And if you remember from that 16 element example, we don't have quite 4 steps. We actually only need to have 3 steps. So each step of the iteration will actually each iteration of the step will actually do one fewer operation than the corresponding iterations of the reduction step. So the first one will actually only do one rather than one step, even though it's actually the second step of the reverse tree. So for every iteration, we're really doing 2 minus 1, 4 minus 1, all the way up to n over 2 minus 1 addition. When we look at the series, we can decompose the two terms of each term here, two subterms of each term, and add up the first part of the series. The first part of the series is really just this 1 plus 1, 2, 4, n over 2, but missing that one term. So if we had a complete series, it will add up to n minus 1. But since we're missing that 1, the first part will add up to n minus 2. The second one is just all ones, and there are log n minus 1 of them. So they add up to log n minus 1. And so the entire sum is going to be n minus 2 minus parenthesis log n minus 1. And when n is big enough, we can ignore the rest of them, and it's order n. It's actually a slightly less work than the original reduction step, but in terms of order of magnitude, they are extremely comparable. So when we add up both phases or both steps of the work-efficient kernel, we end up with operations or additions no more than 2 times n minus 1 additions. So this gives us the order of a algorithm that is essentially doing no more than twice the work that is done in an efficient sequential algorithm. And so this essentially gives us an algorithm that has the same linear complexity of the sequential algorithm. It does a bounded 2 times more work. So as long as we have a lot more than 2 times the resources, which is usually the case in parallel execution, then we can easily overcome the additional work. And this gives us an efficient algorithm. One more important thing that I'd like to emphasize is that it is the trend that's very important when we handle large data sizes. So a work-efficient algorithm becomes even more important when we have very large n. And this is a very typical problem with the big data analysis. A lot of the algorithms are not order n algorithms, but order n log n, such as the work-inefficient kernel that we just discussed. And when n is very big, we start to have very significant explosion of number of operations. For example, if n is equal to, let's say, 1,000,000, and then log n will become 20, and so on. So you can see that when the elements become very big, that multiplicative factor can start to be a very big magnification of the amount of work that we're going to do. So this is actually one of the fundamental problems with big data analysis, because many of the algorithms that we used in the past work okay for modest data sizes because of those log n, or in some cases, these algorithms could even be quadratic, meaning it's proportional to n squared. But as soon as we start to use very big data sets, these algorithms start to exhibit extremely undesirable amount of work, and then start to have very, very significant performance problems. So here are here's another trade-off that I like to raise. The work efficient scan kernel is normally desirable for various reasons. Better energy efficiency, because we use fewer operations for the same to achieve the same goals, and less execution resource requirement. And then, of course, what we just discussed, for large data sets, the algorithm scale much better. However, when we have modest amount of elements, and if the absolute performance is critical, then the work efficient kernel could be a better match, because the work inefficient kernel only requires one step or one phase rather than two-step approach for the reduction. So for modest amount of elements, the work inefficient kernel could actually get better performance, and this is something that you should keep in mind. Now, I'd like to say a few words about exclusive scan. Exclusive scan is also quite frequently used in various computation environments. So the definition of the exclusive scan is very similar to its inclusive scan, but it's kind of shifted. So the definition goes as follows. Let's say if we have an operator, let's call it O, and then an input array of elements x0 through xn-1. So far, it's the same as the definition of inclusive scan. The difference is when the result generated from the operator and the input array will start with 0. So, and then it's essentially the output of the inclusive scan shifted to the right by one position. So this the element 1 will have x0, and element 2 will have x0 up x1. And if we look at the last element, it's really the cumulative operation from x0 all the way to xn-2. And we are missing xn-1. This is the reason why it's called exclusive scan, because the last element of the input array is not included in the final result. So if we look at an example, if the operator is an addition, then the off prefix sum or scan operation on the array 31704163 for the exclusive scan will become 0, and then it will be 3, and then it will be 3 plus 1 equal to 4, and then it will be 3 plus 1 plus 7 equal to 11, and so on. And if we look at the last element, it's really the sum of 31704116, and 3 is not included in that final result. So the question is, why do we have exclusive scan? The reason why we use exclusive scan is that we would like to find the beginning address of the allocated buffers in a kind of a allocation application or allocated resources. The inclusive scan, if you recall, gives us the cut point that we need to make in order to allocate resources. And exclusive scan actually gives us the beginning part of the allocated resources. So that's why they're shifted by a little bit. And in many situations, for example, memory allocation, it's not important where the cut point is, but it's important to give every requesting process the beginning address of the allocated memory buffer. So that's why exclusive scan is also very important. And inclusive scan and exclusive scan can be easily derived from each other, especially if we have already have an inclusive scan implementation. It's easy to produce an exclusive scan by essentially shifting everything to the right and then put a 0 into the zeros position. However, sometimes when this kind of shifting can still be very expensive. So oftentimes we can adapt an inclusive scan implementation to do exclusive scan so that we don't need to do this last step shifting. And so this is a kind of a summary of what we would do to take a work inefficient scan kernel and then make inclusive scan kernel into its exclusive counterpart. Remember, in the end, everything will be shifted by one position. So what we can do is when we read in the global memory contents into the shared memory, for block 0, we will just go ahead and read a 0 into XY0. And all the other threads will load the XY thread in index.x -1. Essentially, they will, instead of reading the corresponding location in the global memory, they will reach to the left by one position and read that into its XY position. So this allows us to create a input list that is shifted by one element and with a 0 padded at the beginning. And for all the other blocks that will be processing the remaining of the list, we would actually use just make sure that all of them reach into the global memory one position to the left and then load into the original XY position. So this creates a input list with a 0 padding and every element is shifted to the left. And then if we do the scan just like we did inclusive, we will be able to generate an exclusive scan result. And if we want to adapt the work efficient kernel, then we need to pay attention to each thread because each thread is loading 2 elements. So only 1 0 should be loaded at the beginning. So we will need to be a little bit more careful in shifting those indices when we do the loading for work efficient kernel. But it turns out that mathematically there is actually a very elegant and intellectually interesting way to do exclusive scan without this kind of shifting in the initial load. And I'd like to encourage you to read the Harris article for a more intellectually interesting approach. However, that approach is a little bit more computationally expensive. So in practice, you may not be clear which one is better. And my suspicion is the shifted version of the inclusive from the inclusive scan into exclusive scan in the loading process is probably as efficient, or in some cases even more efficient than the more intellectually interesting approach. So now I'd like to complete the subject by commenting more about how we can handle large input vectors. We will be building on the work efficient scan kernel. So far, it should be very clear that if the input vector is of up to 2024 for the work efficient kernel, then we can definitely use the kernel to finish the job. However, if we have a much bigger input vector, what do we and we have that work efficient kernel, how do we make sure that we can systematically handle that entire vector? The problem is the entire vector. When we use the work efficient kernel, we're going to be doing the scan on a section by section basis. So at the end of that kernel, every section will have a scan outcome. However, the results of the original big vector should have all the previous elements in other sections all accumulated into any of the later elements. because of the segmented or sectionalized approach, the elements in the later part of the vector will not see the cumulative results of the previous sections. So we need to have a systematic approach to make sure that we correctly propagate, accumulate all those early sections into the later elements. So I'm going to use the next figure to talk through all these steps. And these steps are really just for you to review after you look at the next slide. And we leave it as a homework for you to adapt the work inefficient kernel in the same manner. It's just that there's some details that you will need to work out because of the nature of the kernel, which only have every thread to load only one element rather than two elements, as is the case of the work efficient scan kernel design. So here we show a initial array of arbitrary size. So this is a very, let's say it's a very big array. And then we're going to use up to 2048 elements in each section. So we hand each of these sections to a thread block. So the thread block is going to do a scan on block 0, and the next thread block is going to do a scan on the second section, and so on. So at the end, every section has a localized scan result. That is, each element has the cumulative sum of all the previous elements in that section. And also, even more importantly, the last element of each section, output section, gives the sum total of the entire section of elements. So at the end of this kernel, we will be writing the last element of each section into an array in the global memory. So this array is really the sectional sum of all the sections. And now we do a scan on that array. So we can even just call the same kernel and do the sum as long as it fits into the same tile. So if it's less than 248, then we can just go ahead and call the original kernel and do this. So it's very likely that we can just do it that way. But if the number of sums or number of sections is more than 2048 in the work efficient kernel, we will need to actually do more iteration. We will need to actually potentially do more iteration, and it becomes more complex. So, but for this, the purpose of this course, we assume that we only need to just invoke the kernel once to be able to add the results of up to 2048 sections. And once we finish the scan on the sum array, then each element actually contains the sum total of all the elements in the original array up to the end position of that corresponding block. So this essentially allows us to propagate and accumulate all the previous section results into the later sections. So now, if we take this scan output in the block sum and then add all the elements of each section by the corresponding sum of the previous section. So for example, section 1, all the elements in section 1 will need to add the sum value of the previous section 0 here. And then, so this is shown by feeding that the sum, cumulative sum array element 0 value to all the elements in section 1. And again, also section 2 will need to add all the elements in section 2 by the total sum of all the elements up to end of section 1, so which is in element 1 of that total sum array. So if we do this as essentially a vector addition kernel, and with one of the elements, one of the input to be only one element and the other input is the vector of that section, then we would be able to generate the real scan value for all the elements. So then we can output the result into a final array of scan values. So this completes a vector scan array algorithm that can handle very large inputs. And as you can see, if we have really, really large inputs, we will actually need to be able to take maybe even one more iteration to be able to, in the middle of the process, in order to be able to actually properly handle all the elements. So this can, if you're interested, this will be left as a kind of an optional homework for you to think about how you can write a truly general, truly arbitrary size scan function that utilize the kernels that you have developed in this course. So now we have finished the entire topic of the parallel scan pattern. For those of you who are interested in studying more about this pattern, I'd like to encourage you to read sections 9.4 and 9.5 of the textbook. Thank you.